What do you think? Should we do it?
Between 1 and 2.
Great. Hi, everybody. It's my great pleasure to introduce Steve Cranmer. Steve did his academic education back in the 1990s, a time which I never thought I would long to revisit, but here we are. Got a BS from Drexel in 1990 and an MS from Ohio State in 1991, and then a PhD from the University of Delaware working with Stan Iwaki on winds from rotating hot stars. Oh, his master's degree was in radiative interaction between close binary stars. Steve's worked closely and extensively on both solar and stellar astrophysics. From 1996 to 2014, he was at the Harvard-Smithsonian Center for Astrophysics, CFA. He worked on solar and stellar corona and winds. Some very notable work with Odd van Boylehoyen on alphane wave turbulence in the solar wind and coronal heating models. 2006, Steve won the Karen Harvey Prize, which is the Solar Physics Division AAS prize for early career accomplishments. And in 2015 came to CU as part of the bid that brought the NSO to East, the headquarters of the NSO to East Campus. Steve continues to work on a mix of solar-stellar modeling and observational implication work. The interplay between models and observations is very prominent in the field of solar wind acceleration and heating. He excels as a mentor and as a classroom teacher, and we're very grateful for that. So without further ado, I'll let Steve tell us what he's going to talk about.
Thanks. All right, thanks, Mark. Yeah, I'm very happy to be here. Thanks for the introduction. Thanks for everybody for showing up. Yeah, I'd like to talk about some recent and old research, old questions that we're trying to address with new techniques regarding the corona and the solar wind. I've got an outline, if PowerPoint will let me. Yeah, I'll just give a quick introduction of what these things are, these outer layers of the solar atmosphere, and then start to talk about some of the physics, right? How do we actually get energy from the inside of the sun to the outside of the sun to produce the quantities that we actually observe? How is the plasma heated? And then at the end, talk about some future avenues, because we still haven't solved this long-standing problem of how is the corona heated. First, before I jump into research, I did want to talk about something else. I hope you'll forgive a short little introductory digression into something that is more about the job than about the research, right? You've seen a lot of these talks in the fall. A lot of them are about research. But the job of a professor is about other things, right? There's teaching, mentoring, service, both local, international, national, all sorts of things. And we juggle all those things. Just in the past week or so, I've been thinking trying to think a little more holistically about what are all these different pieces doing together in the same job. There's a reason for it, and I think I've started to understand that reason a little bit more, because I really wanted to take these 4 aspects, research, service, teaching, mentoring, and look at the specific arrows that go between them, right? How does one help, enhance, influence the other? And I actually made a list. I printed it out. I'm not going to show you the whole list of all 12 of those arrows. And it is an interesting exercise to figure out how those different pieces interact with each other and how do they strengthen each other, right? Some of them were easy, right? Research and mentoring are connected very straightforwardly because we mentor students to do research, and the end product are research papers and things. Teaching and research are kind of less clear, right? Teaching basic courses, for me specifically, has helped me learn the fundamentals all over again, and that has helped spur on new research directions. And research to teaching has similar connections. Yeah, I might want to write up something. Maybe I'll crowdsource some of you in this room to give me more ideas of what to put under each of those 12 bullets. But it's been a very interesting experience to see how all these different pieces are not just siloed off from one another, but they're mutually reinforcing. Anyway, back to the research. I do want to talk about that because it's very interesting, right? We observed the sun. The sun is the closest example of a star that we have access to for the time being, right? There are some interesting concepts for interstellar probe missions that might make it to the nearest star. But for now, we have the sun. We can observe it in very high spatial and time resolution, and we can observe it with different wavelengths to basically try to tease out the different layers above the solar photosphere that tell us what's happening above the surface of the sun. We have the photosphere, the chromosphere, where we start to see magnetic structures much more prominently, and where the temperature of the photosphere rises from about 6,000 Kelvin to 10 or 20,000 Kelvin. Then there's this rapid jump to the solar corona, where the temperature is millions of degrees. And there's some interesting history, of course. This goes back to the 1800s. People started pointing spectrometers at the white light that one sees during solar eclipses. And when they started looking at the spectral lines formed by that light, they found some lines that they couldn't identify based on laboratory measurements. So people for several decades thought they had discovered some new element called coronium. But it took until about the 1930s to really understand that the lines of coronium really were coming from very highly ionized species of atoms and ions that we're familiar with: iron, nickel, calcium, things like that. But when they're so highly ionized that 10, 14, 15 of the electrons have been stripped away, that means the temperatures have to be super high, millions of degrees. And that's much higher than the temperatures at the surface. So there was this coronal heating problem that was born. Basically, the analogy is if you're warming yourself up at a campfire and you're moving further back from the campfire, you're feeling cooler and cooler temperatures. But for the sun, as you're moving further and further from the source of energy, the temperature jumps back up. That's the puzzle. And of course, in the 60s, when we were able to send spacecraft up with telescopes that could look at wavelengths like UV and X-ray light above the Earth's atmosphere, we saw a lot more to this million-degree emitting plasma of the corona. Now, together with all this, we also learned a lot about the sun's magnetic field. The sun has a very strong magnetic field. It varies over 11 years between solar maximum and solar minimum. One of the interesting clues that links the magnetic field to the coronal heating problem is the idea that when we look at the strongest patches of magnetic field on the sun, mostly connected with sunspots, which are connected with bright active regions in UV and X-ray, we see more heating. We see higher temperatures and more emission at these millions of degrees temperatures. So the clue number one is that regions with stronger magnetic fields really are heated more than regions with weaker magnetic fields. And of course, the magnetic field extends all the way throughout the sun, right at solar minimum. It's almost like there's a nice bar magnet right there pointing out the north and south magnetic poles of the sun. Well, as we go into the 50s and 60s, Gene Parker realized that if the corona really is this hot, if it really is 1 million degrees, and he worked out some of the properties of the plasma there, he realized that the gas pressure, due to both the high temperature and the density of the material that's there, has to be very high down at the base of the corona But we also know from looking at the solar system that the pressure is very low at the edge of the solar system. So there's a pressure gradient. There's a difference between the high pressure and the low pressure. And my cartoon of an overinflated balloon that is ejecting its air is the analogy there, because you have high pressure inside, low pressure outside. What happens? There's an actual force that accelerates the gas from the high pressure region to the low pressure region. And Parker realized this was necessary. That the sun really does have to be in this continual state of expansion, even evaporation, right? Because it's always losing its material from the surface. This was controversial. His referee's report was initially rejected, and he had 4 years worth of debates with the community about whether this was a real thing or not. But the nice thing is, this was at the dawn of the space age. Marcia Neugebauer and colleagues were working on the Mariner 2 probe that was going to Venus, and when spacecraft started leaving the Earth's protective magnetosphere, the particle and magnetic field instruments aboard those spacecraft detected the properties of the solar wind pretty much just as Parker predicted. So he only had 4 years of controversy, but it was all confirmed. And since then, we've measured it in countless ways. We can send spacecraft out. This is essentially 1 year's worth of data of the solar wind speed, hundreds of kilometers per second, but kind of bimodal between a slow state and a fast state. We can also observe it with coronagraph instruments, essentially telescopes. Why isn't this running? Telescopes where we block out the bright disk of the sun and see the much fainter emission from electron scattering towards us. And with some sophisticated image processing, we can see that there really is outflow happening all over the place around the sun. Sorry about the image, but we can come watch it on my laptop if anybody wants to see it later. So yeah, that was my quick introduction to what these things are. I want to spend time thinking about the physics, right? How much energy is available to produce and maintain these things over, the long time that we've seen them. Well, there is a sort of a schematic picture of the temperature, right? Temperature versus height above the solar photosphere. The solar photosphere is about 6,000 degrees there. And if there was no coronal heating, we would expect the temperature just to drop, just like moving back from the campfire. But we see the temperature increase in several weird-looking ways. Our chromosphere is this little blip of heating up to about 10 to the 4 Kelvin, and there's this extremely rapid jump up to temperatures of 10 to the 6 Kelvin, 1,000,000 degrees. So our questions are here, but it is interesting that there are some aspects of this that we really do understand pretty well. For example, why is there this sharp jump? It's actually a thermal instability. Essentially, when you look at the conservation of mass, momentum, and energy in the corona, you can solve these equations, and you have stable solutions that if you perturb it a little bit, it comes back, or you could have unstable solutions where if you perturb it, it runs away. This is an unstable solution in this middle part here. It's sort of an island between two stable solutions. There's a stable solution of 10 to the 4 Kelvin and a stable solution at 10 to the 6, but everything in between is kind of unstable. So essentially, with a constant heating all the way from the chromosphere to the corona, this bifurcation happens very naturally and spontaneously, and we think we understand it pretty well. In fact, laboratory physicists have another name for it. They call it burn-through, when somebody creates a plasma in a tokamak or something to try to do fusion, and they heat it up. They have to get past this 10 to the 4 point and go all the way up to the 10 to the 6 Kelvin point, where they have to sort of burn through that middle region where it's essentially radiation. It's photons being generated in that middle region that you need to get through before you get to the more stable hot plasma stage. The other question that I think we have pretty good answers for is, how is the hot corona translated into the fast and slow components of the solar wind? Parker's original idea is pretty much still holding. We pretty much understand a lot of it. It pretty much explains about 50% or so of the acceleration that we see. It still doesn't explain the bifurcation into the fast and slow components, so there's still a lot to try to understand how the momentum is generated in the solar wind, and we really want to understand those variations between fast and slow, because that's one of the aspects of space weather forecasting that is crucial for predicting space storms. but we're there at the 50% level or so. But then the question is, where does the actual energy come from? That's another question that I think we have a pretty good answer to. There's a huge source of energy just below the solar surface. That's the convection zone of the sun. The convection zone is a place where photon transport is not really very favored. What's happening is very much what's close to what's happening in a pot of boiling water. You're heating the bottom, and spontaneously forming are these little blobs. The hot blobs tend to rise up, the cool blobs tend to fall down, and in a net sense, there's a transport of thermal energy from the bottom to the top. And through the convection zone, the sun is basically sending all of its energy, all of its luminosity divided by the surface area, which we could write in terms of nice metric units. Kilowatts per meter squared is something like 63,000 of those. That's just a unit that I'm going to choose to follow through, because once we get to the surface, then things are a little different. At the photosphere and above, it's no longer convectively unstable. The rising and falling blobs cease at the surface. Most of that energy is converted to photons, and we see the bright sun. We see this luminosity mostly as photons, but there's a small little remnant that we see at the photosphere. When we look at the surface of the sun, there's an observation. We see the tops of those boiling blobs, and the amount of kinetic energy in those blobs expressed as a flux is a small fraction of the 63,000. It's about 500 kilowatts per meter squared, but it's also something that we understand pretty well. All right, then what happens to that 500, right? How much of that energy makes it from the photosphere up to the corona? So, well, then we have to start thinking about the magnetic field, right? The magnetic field is threading the surface of the sun. It's always churning and changing. And, astronomers, when they want to explain something, they often make simplified cartoons just to try to leave out all the unimportant things and just leave in the important pieces of the physics. So let me show you the solar physicists' attempt at a simplified cartoon of how the magnetic field threads the surface. Yeah, sorry, that's as simple as they can get sometimes. This cartoon by Sven Wedemeyer has been sometimes called a confusogram because there's just a lot going on, and it's really hard to disentangle these different pieces of how the magnetic field and the plasma are all varying. The one thing that you can do, if you just squint your eyes a little bit and ignore 90% of the details, one thing that you see is that the magnetic field lines, which are these thick white lines, up in the corona, which is up at the top, the region that's filled by magnetic field, if you trace it down, it only goes down to a small fraction of the surface area of the sun. So the one thing we can say is that only about 1 to 10% of the surface is essentially magnetically connected to this corona and the regions above. So the energy that we have to work with isn't this 500, it's 1 to 10% of that, 5 to 50 kilowatts per meter squared. We've reduced it a lot, but that's still a decent amount of energy. So what's actually happening here? These magnetic field lines are poking up through the surface. They're being jostled by all the motions of the tops of the convective cells. And essentially what we're seeing for this energy flux is essentially a magneto-hydrodynamic pointing flux. It's essentially how much magnetic energy is being transported upwards by these motions. And we can measure these things. There's been some great work done by Sam Van Kooten in his PhD work back in 2022. He worked out a lot of the details of computing these fluxes based on observations of magnetic structures that are moving around horizontally on the sun. One interesting thing he discovered is that prior observations mostly only took account of the fact that the small magnetic elements, that their centers were moving around, right? That essentially these were magnetic flux tubes that were being jostled back and forth. That provided a certain amount of energy. Sam looked at much higher resolution simulations that hopefully soon DKIST will start to see from the NSO, and found that there were other types of motions, not just motions of the centroid of the feature, but motions that involved, the feature being distorted into ellipses or higher order structures, or maybe the entire area of the feature going up and down. When you take into account the energy flux carried by those, it pretty much rivals what earlier generations of observations saw. So we might even be seeing almost as much as double of the amount of energy once we really take advantage of DKIST's high resolution. All right, but still 5 to 50 kilowatts per meter squared is our ballpark. And the question is, do we really have a problem? Is there a coronal heating problem? There would be a real problem if this was not enough, right? We want to know how much does it take to heat the corona? Is this enough to heat the corona? I can point to other work during their PhD work of Momchil Molnar and Chris Gilly, and also subsequent work as postdocs, where they were studying various aspects of this. So there's a lot of aspects of trying to track the magnetic motions, finding out what fraction of that energy is available to heat the corona, but then using observations of the heating itself to figure out how much heating is needed. The energy required to heat the corona is actually of the same order of magnitude or a little bit less than what we know to be available. That's a good answer. That's nice. So if the question, do we actually have a problem here? I think the answer to that is no, but there's still this intermediate step where we've just jumped totally over the physics, right? We haven't said, how does this magnetic energy get converted into the thermal energy for heating the particles up to millions of degrees? There's a miracle in there, and we really need to be more explicit about that. That's the next step, right? That's the next step of the talk. So how is the plasma actually heated? That's what I want to think about. Okay, so we have to tell more stories about what's happening here. Story time, proposed heating processes. I'm going to be talking about these two timescales. You know the old classic, right? A tale of two timescales. We're just talking about characteristic times over which things happen at different levels of the solar atmosphere. So I've got these two timescales called the photospheric time and the Alfvén time. These could be called different things, but basically the photospheric time is how long does it take for the motions at the top of the convection zone to jostle those magnetic fields around. And then the second Alfvén time has more to do with the corona above it, right? How long does it take for information to propagate along the magnetic field, say along a coronal loop or an open magnetic field that goes out into the solar wind? So comparing those two timescales with each other tells you very different stories depending on which one is the bigger of those two quantities. So for example, if the photospheric driving time was very short and the time it takes information to propagate along the field in the corona was long, we have this one scenario that I've sort of illustrated like plucking a taut guitar string, because this is a scenario dominated by waves. We're essentially saying that the motions at the base are very rapid, pluck, and then the information, the oscillations propagate along the magnetic field like a wave on a guitar string. What happens in a real system, not just an ideal textbook system, is that waves don't go on forever. They eventually dissipate, they damp out because of imperfections in the plasma, particle-particle collisions or wave-particle interactions in a plasma. But there's ways that waves damp out, and that the energy in the oscillation gets converted into the randomized energy of the particles for heating. So that's the actual mechanism of coronal heating when the photospheric timescale is much smaller than the Alfvén timescale. Waves propagate up, waves damp, and that energy goes into the heating. So these are often called AC, alternating current systems, just because AC involves oscillating waves, and there's a similarity there. That's one extreme. The other extreme is when the photospheric driving time is very slow, but the time it takes information to propagate along the field is very fast. So that's sort of the opposite. So what's happening here, and this is sort of the same type of picture as up here, but I've sort of taken a scissors and snipped it in between and taken that other end and put it up at the top, just so we can see how the field connects from one end to the other. But if the motions are very slow and there's a lot of time for the field to react to it by sending information back and forth, then what happens is that the field gets slowly tangled, twisted, braided, and almost knotted into complicated configurations like this. Now, at certain positions in the field, the magnetic fields get so tangled and knotted up that you have fields in opposite directions being pressed against each other. And what plasma physicists have found is that when that happens, we have this phenomenon called magnetic reconnection, where part of that magnetic field is actually annihilated, and in a small little bursty region, the magnetic energy is rapidly converted into particle heat, some photons, various forms of energy, but you can get heating in a very sort of sparky and intermittent way when you have this type of buildup of magnetic stresses. This is called a nanoflare idea because each little heating event is very small compared to something like a solar flare, but taken together, there might be enough energy there to heat the corona. And again, the opposite from AC is DC, direct current. Stressing models is what these are. And there's other versions of this, right? What I showed here was a very randomized type of tangling and braiding. There are other places on the solar surface where it's much more organized, right? Where there's a much more sense of an overall helical buildup of magnetic stress. And when that dissipates, there's some interesting math there. The dissipation actually obeys an interesting fourth order partial differential equation called hyperdiffusion, which is kind of fun. But yeah, there's a lot going on there. Now, okay, this was story time. Now it's reality time. Here's the problem. For the real solar atmosphere, we don't get this clean AC or DC limit, because when we actually measure these time scales, they're of the same order of magnitude of each other. So we don't get the pure AC, we don't get the pure DC. We get a hybrid kind of both. And the language that is often used for this combination of waves and nanoflares that has developed over the past 20 years or so is MHD turbulence. Turbulence is basically a stochastic way of a plasma responding to forcing, where large structures collide with each other and form smaller and smaller structures in sort of a spontaneous way. But that seems to be what's happening for the sun. You have some element of the alphane waves being generated by jostling the magnetic fields, but the timescales aren't quite right for them to just take their time and propagate along the field. This turbulence takes over because the field also gets twisted. And once it gets twisted, you get this intermittent nanoflare-ish type energy release with magnetic reconnection. So it's really both the wave and the nanoflare picture that are sort of happening at once. There's a whole literature trying to explain how it works, some simulations that should have kept going. But yeah, showing how the magnetic fields get twisted up via the propagation of these waves from the bottom to the top. So yeah, this has been a successful way of understanding coronal heating. It's been an ingredient in many 3D computer simulations. And these simulations have come quite far. I can show you some snapshots of some of the results. Some of these computer simulations really just start with the convection at the bottom, and they put magnetic field in, and spontaneously coronal loops and coronal structures form, which is great. The problem, though, is that these computer simulations have a finite resolution, right? They're built with numerical grids, either with finite differencing or finite volume or spectral methods, but there's always a finite resolution, and that finite resolution really has not yet gotten down to the point where we can really resolve the scales, those the smaller of the tau alpha versus tau photosphere. We really haven't gotten down to the point where we can really resolve those and see the actual real physics that's causing the coronal heating. The finite resolution is sort of shortcutting the process, and much of the heating that you see in these simulations is essentially numerical viscosity, numerical resistivity, things like that take over and produce the heating. You know the heating has to happen somehow, but these simulations aren't really showing you how it really happens down at the smallest scales. So these are great. We've learned a lot from them, but there is another approach that I'd like to talk a little bit more about. It's something I'm calling the sort of a corona construction set model, because rather than just building a simulation in a box, you can be a little more intentional about building a simulation of the corona. For example, you can start with the magnetic field. We have nice measurements of the magnetic field at the photosphere and nice methods of extrapolating them out into the corona. Those magnetic field lines are something that we can think of as sort of a skeleton of the model. And then along each of those bones, along each of those magnetic field lines, we can apply one-dimensional models of coronal heating and basically paint in the plasma properties, the temperatures and the densities, the abundances, as the result of those individual 1D models, sort of like musculature on the bones. And then if you do that throughout your entire volume, you have a three-dimensional description of the corona, and then you can simulate what observers, say in the ultraviolet or X-ray, would see if they were to look at that system and compare it to the observations. But the nice thing is we have complete control over these 1D models so that we can vary their parameters in an intentional way and really try to hone in on the physics that heats the corona. This has been done for about 25 years now, and I think there's a lot to say for these models. It's potentially global. You can do the entire sun. You can use it to essentially test any theory you want. And essentially, because you're modeling these magnetic fields almost in an analytic way, you can almost have potentially infinite resolution in space and time. Now, there's shortcomings too. I don't think I'll go through every item in this list here, but sometimes the coronal heating that has been used in the past has been kind of simplistic, just saying that the heating goes as the magnetic field to some power and the length of the loop to some power. There have been coarse grids in both the parameters and the data, and some other physics shortcomings. But this is something that a few years ago we decided to revive, because there's some interesting ways that I think we can do a lot better with this. For example, the coronal heating rate. This jumble of an equation here is, I think, a much more physically motivated version of the heating rate. Essentially what we're doing is starting with that Poynting flux that we know is available at the base of the corona from the stirring of the magnetic field. That's this piece over here on the right. And then we multiply it by some efficiency factor that's less than 1 that depends on dimensionless ratios of the time scales and corresponding length scales of both the driving and the corona. That ended up being a very neat way of expressing this, because if you go into the literature of the past 50 years or so of coronal heating literature, when people have proposed solutions to the coronal heating problem and boiled them down to equations, it turns out that many of those can be expressed in this general way, but just with different exponents, m and n, on those time scales. It was really fascinating to see so many proposed things by Parker, Alfvén, many people throughout the years fall into place with specific values of these m and n exponents. And also at the bottom, another thing one could do is take these numerical simulations and back out what kind of exponents would be required to reproduce their properties. So you can get values of the exponents there too. Now, rather than just showing you this table and having you squint, another way of doing that would be to plot these different regions of m and n versus one another, and you can see that the different classes of models, like the DC models, the AC wave models, the turbulence models that sort of bridge between them, they all sort of live in certain regions of the parameter space, and this hyperdiffusion model with the helical twist relaxation is over there to the left. The things from the numerical simulations are in the middle there, of course not helping us choose between the models, but that's okay. And there's a few other theories that don't just give you a specific prediction. Sometimes they just give you a linear line. This model of imbalanced turbulence, for example, says that you could be anywhere along this line, but not off of the line. It's nice. We have a lot of good inputs there. But now the idea is to freely vary these m and n exponents. So for every point in this plane, we can build a model, one of these construction set models, simulate what it looks like with telescopes, and compare it with the real data. That's what we're trying to do. And I guess that's what I'm saying here, right? So what we did was we picked two specific dates, one at solar minimum, one at solar maximum. We found nice high-resolution magnetic fields from the NSO GONG ADAPT magnetogram data products, extrapolated those out, and then started painting on the coronal properties according to those models. And then we have the data from SDO's AIA telescopes that look in the EUV, 7 different filters, narrowband filters in the EUV, and in the X-ray, Hinode's XRT telescope, with 9 different bands in the softer X-ray. And oh yeah, and I don't know if you can see the little cyan circles on these. Rather than trying to build up complete pictures of the high-resolution pictures of the corona at each of these times, we wanted to keep the data processing a little more realistic. So we just picked 22 points. We started off with a sort of a hexagonal grid and then picked a few extra points in interesting locations. And for each of those points, though, we have to do a full line of sight integral of all the different locations at high resolution from infinity all the way down to the surface of the sun to try to simulate what kind of photons are going to be emitted by each of these pixels, essentially. So that's easy to do for both of these telescopes. There's a lot of information out there about how the different filters respond to different temperatures. So for example, that's what I'm sort of showing here as a function of the log of the temperature. The brightness shows what the 7 different AIA filters and the 9 different XRT filters, what temperatures they most respond to when you're observing the corona. And as expected, the extreme ultraviolet is most sensitive between about 5 and 6 million degrees. The X-rays are sensitive to higher energy plasmas, with temperatures up to about 10 to the 7 Kelvin. You have to take into account the time-dependent instrument degradation that's going on up in space because these detectors are continually losing efficiency. So we have to fold that in. This plot was made for a specific date, and it would look slightly different on a different date. And there's one other piece of physics that gets folded in here that's important, and that's this nanoflare idea. Remember, we said that many of the coronal heating models are not just a steady heating. They have this little bursty, sparky emission of photons. And if you were, say, to look at one location and look at the temperature, you would see spikes, and then it cools down. Spikes, cools down, spikes, cools down. That's what nanoflares do. It's very intermittent. So for example, when we look at a pixel and we do any kind of averaging in time or space, even that averaging as we look along the line of sight, what we end up seeing is signs of what we call a multi-thermal plasma. Because essentially what we're seeing is some average of this sparkiness. We see many temperatures coexisting in one pixel. So what we decided was to do sort of a statistical approach to this. There was somebody named Will Barnes who actually mapped out the statistics, the probability distributions of temperature that given a specific nanoflare model, what kind of distribution of temperatures would you see? And he found that as the time between these energy release events, as that time gets longer, you get a broader distribution. That sort of makes sense because if there's a lot of time between events, it can heat all the way up, it cools all the way down, heats all the way up, cools all the way down. So you see all those temperatures. If the time is very short, it heats, cools a little, heats again, cools a little, and the distribution of temperatures is much narrower. And that's what they found. Going from the black curve to the red curve, they found that those are longer and longer mean times between the bursty events. We fit it with a model inspired by subdiffusive transport, and we implemented this, and we implemented it in those temperature response functions. It turns out to be an elegant way to do it, because if all you're looking at is a plasma of a single temperature, you see what I showed before. But if you're looking at this sort of multi-thermal plasma where there's a specific time between events and there's a probability distribution of temperatures, you'll end up seeing a broader distribution. And I can sort of flash back and forth there to show you how convolving those two distributions together can give you a nice way of simulating the EUV and X-ray emission from them. So we did this. We went ahead, we took our solar min and solar max models with our 22 or 25 pixels, and each one of those had 9 plus 7 filters from the different spacecraft. So we had between 200 and 300 specific unique data points to compare between the observations and the models. Down here is an example showing that comparison. The black points are one example simulation. The red points are the observed data. We split off the active regions from the non-active regions because we found the active regions weren't agreeing quite as well. So maybe there's some different physics, maybe this twisted hyperdiffusion, which we still haven't really included properly, might be happening in the active regions. But outside them, it's doing really well. And this was sort of a chi-squared minimization problem. We ran hundreds of models with different values of m, n, and different values of the time between the nanoflares to make sure that was covered, different values of the overall normalization of the heating rate, and tried to find the best values of m and n, the minimum of the chi-squared. The upshot of that was that I think we're on our way to sort of narrowing down the physics of the coronal heating. Here's that m and n plot again, and the blue points are from the solar minimum comparison between the data and the models. The red are from the solar maximum, and they really do seem to be pretty close to that diagonal line from imbalanced turbulence. I have two versions of that line with some error bars on it. There's a slight green error bar on that one to the right that you might not be able to see, but it's coming really close to these models. Imbalanced turbulence is basically the idea that the turbulence is driven by waves going up one side of the field, one side of the field lines, but then the waves coming back down are weaker. So when the wave packets combine with one another, it's a strong one combining with a weak one. That's the imbalance. Yeah, it was kind of amazing that these fell so close to this predicted curve. So there's some preliminary answers about the coronal heating problem, maybe. There's a lot we left out. We left out the twisted flux ropes with the hyperdiffusion. We left out some of the physics of the solar wind for the open field lines. But I think this is a nice preliminary look at the coronal heating. Yeah. So yeah, the final part of the talk, I just wanted to talk about some future directions. One interesting aspect of all of these temperatures, every time I've said the word temperature so far, I've been making the assumption, and it's been in your heads too as you've been hearing it, that all of the different components of the plasma have the same temperature. Right? That's usually what's happening in most gases and plasmas and fluids that we deal with. All the different species, all the different atoms and ions and free electrons, if it's ionized, they're all in thermal equilibrium with each other. But in some parts of the solar wind, that's not the case. Here is another plot of temperatures versus height above the solar photosphere that have separated out the temperatures of the protons in red, temperatures of the free electrons in blue, and because we have good measurements, temperatures of either 5 times or 6 times ionized oxygen, just because they correspond to oftentimes to either very, very abundant ions that you can measure with spacecraft or very bright spectral lines that you can measure in the UV. And those 3 curves are not on top of each other. There is not a thermal equilibrium there. The oxygen ions are superheated in the upper corona. The oxygen ions actually reach temperatures of about 100 million kelvins. That's even hotter than in the core of the sun. The protons remain hotter than the electrons by about a factor of 2 or 3 throughout a lot of the outer part of the corona. And what we're seeing here, if you look at the radial dependence here, I think David Malaspina talked about this last week, when you look at the radial dependence of these temperatures, they're actually falling off a lot more shallowly, a lot more flatter than if you just heated the corona and then we're just done with it. Right? If you heated the corona and the plasma expanded in an adiabatic way with no additional heating going on, the temperature would drop off much more steeply. But we see these effects of energy being continually dumped into the particles from something, from whatever was happening in the corona to heat the corona. It's still going on 10, 100, 1,000 solar radii above the surface. So we're looking at this. There's a project by Lily Struss that's currently going on that we're looking at new ways of computing the collisionless wave-particle interactions, specifically the ion-cyclotron interaction between high-frequency alphane waves and the Larmor motions around the field that allows for efficient energy transfer between the waves and the particles in a way that actually produces different temperatures for the protons and the ions and the electrons. And yeah, going beyond the textbook methods of computing this type of heating, Lily is working on. There's also some interesting work going from the magnetohydrodynamics to radiation hydrodynamics. Some past work by Alicia Latimer, who graduated in 2024, on the radiation matter coupling in stars and in AGN outflows by looking at the opacity in millions of spectral lines. That's another interesting avenue for the coupling between different types of fluids, right? This time radiation and ionized particles. And there's a fascinating project that I've been waiting to start. Hopefully I can figure out before I retire this idea of how does this process work in a similar collisionless medium as this, right? When the particle-particle collisions are so weak that the velocity distributions are no longer Maxwellian, right? It's out of equilibrium like it is in the solar wind. There's some really great stuff to do there, and I'm hoping it could be done sometime. Plenty of other things are happening in the corona, though. Daniel Mendoza is working on some models where we're trying to improve the extrapolation. Remember I talked about the skeleton, where we have the measurements of the magnetic field on the surface, and we extrapolate it. Many of the current space weather forecasting methods use a relatively simple means of extrapolating that magnetic field called the potential field source surface method. The problem is it's bad. It doesn't reproduce what the magnetic field actually looks like. If you were to use these straightforward, commonly used extrapolation methods and try to predict what total eclipses look like 3, 4, 5 solar radii out, it wouldn't look anything like them. Daniel is looking at some other extrapolation techniques that we can fine-tune and try to compare the shapes of the magnetic field measured during total eclipses with that coming from these models. And the nice thing about these models is that they're similar in technical scope as this PFSS model, so you don't have to do a full-on MHD simulation to extrapolate the field. It's just another type of mathematical problem. And I can't let this talk go without talking about PUNCH. PUNCH is the polarimeter to unify the corona and heliosphere. It was just launched earlier this year, a set of 4 small satellites that is essentially doing this coronagraph type observing of the very low intensity white light that's scattered by photons coming from the sun, and the electrons in the corona scatter the light towards us so that we can measure the electron density of features in the solar wind. The amazing thing about PUNCH is that it has the biggest dynamic range in distance, right? The actual sun is this little yellow dot at the center here, and it measures from 5 solar radii out to 150 solar radii. It has different telescopes to fill in different pieces of that puzzle, but it's the only mission that does it regularly. You know, every 4 minutes or so, you get a picture like this. And yeah, it's been running since the summer, I guess, when they've checked out all the instruments. And currently, I'm working with Treston Simon, Chris Gilley, and some others in trying to build additional 3D construction set type models of the density in the corona to try to better understand when we see little features moving in and out in these movies. This will be a movie someday. We can track the velocity in the solar wind. We can see things going back down to the sun, and we're trying to map out some of the critical surfaces, like the sun's alphane surface in the heliosphere. Yeah, there's really a lot of great new observations coming along. I can't also go without mentioning DKIST. DKIST is continuing to push the boundaries of spatial resolution. I don't know how well you can see this movie. This is a recent movie just from earlier this year from a test instrument that was installed on DKIST to really push the envelope to really get down to the diffraction limit of this telescope. These large-scale bubbles are those small bubbles at the top of the pot of boiling water that I showed earlier, the solar granulation. And the incredible amount of filigree structure that you see in these lanes in between. Of course, it pauses on one blurry image, but when you see the movie, you can see a lot more fine scale structure billowing in those tiny little things that were just mind-blowing when we first saw them a few months ago. There's also other ways of looking at the white light off to the side of the sun by trying to emulate solar eclipses. ESA's Aspix instrument on Proba 3 is now sending back data, and they have tried to solve this problem of diffraction in a coronagraph. You know, if you block out part of the sun, there's often diffraction around the edge of that occulter. But if you move the occulter much further away from the telescope, much like the moon is far from the Earth when we see a true solar eclipse, the images get crisper. They have now put the occulter on a separate spacecraft. And during some times when they get these images, these two spacecraft are flying in formation just at the right way to block out the sun. And eclipse quality coronagraph images are happening. A lot of great stuff. Yeah, I guess I'm sort of winding down. I do want to basically also say how thankful I am to CU for this opportunity of being a professor. There's some really nice sort of privileges of being a professor. Doing all this research is great and I enjoy it, but also every so often it's nice to be able to go off on a tangent and explore something that one gets curious about. So over the years I've played around with some fun ideas that I think have paid off. Like for example, computing the visible light perceived colors of astronomical objects. For example, a brown dwarf. Did you know if you were to go next to a brown dwarf, take a look at it, it would be purple? That's what you can figure out by taking the spectra and convolving them through what the eye actually perceives. I've got a Python code up on Zenodo if anybody has their own spectra that they want to see what color it would look like if you could see it up close. I've gotten a chance to play around with and learn about mathematical topics of infinity and also a little bit of planetary physics. The idea of looking at active asteroids. There are some Mercury crossing asteroids that get very, very close to the sun, and they grow tails and comas just like comets do, but they don't have any water, they don't have any CO2. It's the rock that's sublimating to generate these clouds. Really kind of cool. All right, I guess I'm sort of, like I said, I'm winding down. The other thing I want to do is also express gratitude for, as I say, being part of a chain of mentoring that goes both backwards and forwards in time. I've been very lucky to be mentored by some great people. Mark mentioned Odd van Ballenhoen, who passed away in 2022. I also just learned a couple weeks ago that Tom Holzer, my grand advisor, just passed away recently as well. Yeah, some awesome people. And then in the other direction, into the future, some awesome students, some of whom are here in this room, that are the next generation. And I think that's a good place to conclude. I mean, I could just say that, you know, these solar problems, right, the coronal heating problem, solar wind acceleration problem, they're not yet solved, but I think we're including more and more real physics in these models, and that's doing a better job at helping to explain what we see. Plenty of past, current, and future telescopes and instruments that are involved there as well. And I'll then just leave you with a couple references if anybody wants any more info. All right, thanks.
Thanks, Steve. Okay, we have some time for some questions. Usually we try to take questions from students first.
Hi, I was hoping you could explain some more about the nanoflares. Basically, like, why does magnetic reconnection happen instead of the fields just getting more twisted? And then when it does happen, like, what is transferring the energy to the particles in the solar wind?
Yeah, so magnetic reconnection is sort of a stopping point for the evolution of the magnetic field, because at some point the presence of particle-particle collisions, just like when I talked about the waves eventually damping out, it's a source of, I could use the word friction, right? It's the fact that you have these particle-particle collisions generates things like friction, viscosity, resistivity. There's a whole bunch of names for it, but it's basically ways that that entropy starts to take over, right? The second law of thermodynamics, you know, you can't just have these ideal fields flowing around forever. At some point, because it's individual particles moving randomly, entropy has to start to win. And at these small scales where fields get pushed together, it's the resistivity aspect where little electric currents start to flow that these individual random particle motions just mess it all up and essentially break the field lines. I think that's a decent way of explaining it.
Thank you for the interesting talk. And I understand still so many problems in solar corona heating, but I'm asking, what's the problem when if we apply to like corona heating to other stars, like for example M dwarfs? What's the most difficulty?
Yeah, I should have had a slide. I've tried to look at existing measurements of both X-ray emission from the coronal heating of other cool stars and their mass loss rates. I think in the vicinity of the sun, the FG and K-type stars, I think a turbulence type model like the ones we've developed for the sun work pretty well for predicting the properties that we can observe of other stars. M dwarfs are weird though, because M dwarfs, if you follow that same solar paradigm and go all the way down to the M dwarfs, an M dwarf has a very low luminosity, right? So the amount of energy available from the convection, even though it's fully convective all the way down to the core, that total amount of energy is orders of magnitude less than for a solar type star. And if you were to try to predict, say, a stellar wind mass loss rate, just from that lower amount of flux available, you would get something much lower than what we've observed in some of these cases. So there's got to be something else happening to keep the outer layers churned up that is not just the standard flux transport due to the convection. And I'm not sure what that other thing is, but yeah.
Is there enough momentum deposited by the imbalanced turbulence to drive the wind?
There is a fraction of that momentum that can go into accelerating the high-speed streams. Right? This is this idea of wave pressure acceleration. Right? The fact that if the waves, and this actually doesn't even depend on the waves being damped, if the waves are propagating out and conserving energy, but they're propagating through an inhomogeneous medium, they can transfer momentum to the particles and accelerate it. And models that try to explain the 700 to 800 kilometer per second fast solar wind need that as a component.
So the reason I'm asking is that we had a graduate student who's a physics graduate student, Leah Hankla, who did some collisionless simulations of imbalanced turbulence, but in the relativistic limit. And there, the momentum deposition is extremely efficient, but it seems to become less and less as you get less relativistic. So that's why I was wondering how low it was in the solar limit.
I should look at that. In the solar wind, there is a collisionless limit to that momentum deposition due to wave pressure, and just like the radiation matter coupling in the collisionless limit, it hasn't really been studied. There was a PhD thesis by Chuck Goodrich from the 1970s that tried to deal with this, but hasn't really been followed up on since.
Yeah, great talk.
Thanks.
I'd like to pursue the question of the relationship between the two timescales, photospheric and alphanic. And you say that those two timescales are approximately the same in the corona, but the density in the corona varies by orders of magnitude as you move away from the sun. So you have a situation in which you're probably, the two timescales are one way low in the corona and the other way high in the corona. And it seems to me as though models that just assume a DC type mechanism or an AC mechanism are unrealistic. You need to convert from one mechanism to the other as you move outward in the corona. Have people pursued that at all?
Yeah, I think that's sort of hiding in this other dependence that I didn't talk too much about, right? When we generalize, when we try to find how these models work in terms of the simple ratios, there's the time scale ratio, but there's also the length scale ratio too, of the driving length versus the loop length. And the fact that, say, the alphane speed varies along the loop due to this large density gradient, I think is encoded in that term there, at least in a few of those DC type models.
Steve, is there a difference between solar minimum and maximum in the characteristics of the heating process, or is it just an issue of magnitude and quantity of heating?
I think we're going to have to do more studies and to look at more timescales throughout the solar cycle to really pin that down. Yeah, I mean, it seems like as you go more towards maximum and include the active regions, it gets more towards that DC side, and when we're at the quieter stage, it's more towards the AC side. But we need to dive into that.
One last question.
Okay. Thanks, Steve, for a great talk. I have two questions, and I'll ask them both, and I'll let you choose which one you want to answer. So in the confusogram, a very small fraction of the flux at the bottom leads to all of the flux at the top. What about the other regions at the bottom? What happens to the energy there? Is any of that able to leak out into the corona with cross-field drifts or things like that? That's one question. The other question is in your digression at the very beginning about service, mentoring, teaching, and research. What was the hardest of the 12 links for you to make?
I'll answer both. I mean, for the second one, I think it was mostly the things that connect to service. But yeah, things that with not the natural connections. But again, I've got ideas, and I think I do want to crowdsource this and get more ideas, and maybe there's a way to publish that or something. But about this thing, yeah, there is so much happening in the chromosphere in these weak field regions that aren't strongly connected to the solar to the upper corona. A lot of Momo's work continues to focus on this region with DKIST and other telescopes. But yeah, it's a mess.
Great. Let's thank Steve again.